Welcome back to Chemistry 4300. In this video we're going to continue in Chapter 1, and now we're going to focus on how we can describe the equations of motion of a system purely in terms of the kinetic and potential energy functions. Now this is going to be particularly important in quantum mechanics, but I'm going to show you here how we can also do this in classical mechanics. Now you're used to looking at the problem in terms of force is equal to mass times acceleration, which I've rewritten here as mass times acceleration minus the force is equal to 0. That's a vector differential equation that you have to solve. And the way you would do it is you would write it out purely in terms of the components. So we would have the x component, which is the mass times the x acceleration, plus the derivative of the potential with respect to x, which is minus the force. So that gives us this term. We do the same for y, we do the same for z. And what we have is three differential equations. In fact, what we have are three coupled differential equations, and that's because x, y, and z is present in the potential function for all three equations. Now notice here I'm using this dot notation, so for the time derivative. So x dot is dx dt, and x double dot is the second derivative of x with respect to time. So that's what I'm using over here. Now what I want to do is to try to generalize these expressions for a system of particles. So this is just for one particle, but what if we have a system of n particles? So if we have a system of n particles, we'd have to write this out, x, y, z for each particle, and we'd make then for first particle, second particle, third particle, all of these coupled differential equations. But I want to try to write this more compactly as we go forward here. So what I'm going to do is I'm going to redefine my notation here. So this may be a little bit confusing, but this is the Newton's law for just one component. And the way I've written this now, I'm going to replace, say for example, for the particle A, which has mass A, I'm going to define x1, x2, and x3 to be the x, y, and z coordinates of particle A. And I'm also going to define m1, m2, and m3 to be the mass of particle A. All right? And next, for particle B, for example, I'm going to take x4, x5, and x6 and define those to be the x, y, and z positions of particle B. And I'm going to take m4, m5, and m6, and I'm going to define those to be the mass of particle B. Okay, so you can see the way I'm doing this. We continue on with all the particles. That way I end up with one equation that I can write, which is indexed with I, and now I runs from 1 to 3 times the number of particles. Okay, so instead of in the previous slide having to write down 3 equations for every particle, I'm writing down one equation which has an index that goes from 1 to 3n. All right, so this is just to make things a little more compact. Now, what we're going to do then to get to where we want to go here is we're going to start out with the kinetic energy, which is going to be a function of the velocities, which 1/2 mv squared, but I'm using the dot notation here. And so the total kinetic energy will be 1/2 mv squared, or x dot squared, and then summed over all of those components. Now, if I first take the derivative of this expression with respect to one of the velocities, or one of the xi dots, then you can see that it's going to take this sum and just give us just the one that's the xi dot there. So we're going to end up with one term out of this whole series. Next, I'm going to take this expression and I'm going to take its time derivative. And if I take its time derivative, then I'm going to take the time derivative of the x dot, which is going to turn that into x double dot. So now I've taken the derivative with respect to x dot, xi, and then xi dot, and then the time derivative of that, and I end up with this whole expression equals the mass times the acceleration, right, along that direction. So if you go back to my original equation then that I wrote with the mass times the acceleration of the component plus the derivative of the potential, I can now rewrite that as saying this part here I'm going to identify as this derivative of the kinetic energy. And of course, the potential energy is already in there. So now I have an expression which is identical to this, but it's written entirely in terms of the kinetic and potential energy functions. All right, so this move on to the next slide here. So here it is, summarized. We have the ability for a system that's operating under conservative forces, to write out the entire set of 3n coupled equations. All we need to do that is we need to have an expression for the kinetic energy and the potential energy. And these are entirely scalar functions. So we don't need to work with vectors anymore. We can work with just a series of coupled differential equations and starting with the scalar functions that describe the kinetic and potential energy for that system. So this is a really nice simplification and sort of way to generalize the problems. And now, you may wonder, like, well, why didn't Newton do this in the first place? But remember, the concept of energy actually didn't show up until about 100 years after Newton wrote down his Principia. So he wouldn't have known or thought maybe to do it like this. But this approach, this kind of approach, just sort of gives you an idea of that the equations of motion can be described entirely in terms of kinetic and potential energy. This is not the way it's generally used. There's other formulations of ways of doing this. One is called Lagrangian mechanics. Another one is called Hamiltonian mechanics. And these are even more versatile than what I've written here. But I just want you to get the general idea that we can describe what's going on in terms of these two functions of the system. So let me just give you an example how you might use that. Let's say that you want to determine a trajectory of a ball that's initially thrown straight up in the air with some initial velocity, and we're going to neglect air resistance. So this is a one-dimensional problem. It's probably the simplest problem you might be able to imagine. So I'm going to write down my equation. It's only in one dimension, so I only have z for this. And I'm going to write down the kinetic energy. And the kinetic energy is 1/2 mvz squared. So in my notation now, it's 1/2 mz dot squared. And the potential energy will be the potential energy from the Earth's gravitational field. So we're going to write down that it's mass times the Earth's gravitational field, the acceleration due to the force of gravity, g naught, and then times z. So this number is, what you probably remember, of 9.8 approximately meters per second squared. So if I first take this guy and I take the derivative with respect to z dot, then that just gives me mz dot. That's simple enough. Then I'm going to take the time derivative of it, and that's going to take my z dot and turn it into z double dot. That's an acceleration. And then, of course, for the potential, I'm going to take the derivative with respect to z, so that's going to give me just back mg naught. And then I'll take these two guys, plug that into there, and that into there, and what I get is the differential equation of motion for this problem. Now I just have to solve this differential equation. So I'll leave this as a homework assignment for you, but the solution should look like this. And if you wanted to plot this, then you should get the height, for example, as a function of time, should have this be this parabola that you get just by plotting out this equation. Okay, so that's just sort of working through probably one of the simplest examples, but to show you that we can describe the motion by just having the kinetic and potential energy functions. Now, we're going to be dealing with a lot of differential equations, so I just want to remind you of some terminology that we're going to be dealing with. And so first of all, when you see a differential equation, we may talk about the order of the differential equation. The order of the differential equation is just the order of the highest derivative in the equation. So we're going to be dealing with ordinary differential equations and partial differential equations, and generally speaking then, the equation will be some function of a particular function and its derivatives. So if our differential equation is linear in the function, or its first derivative, second derivative, or its nth derivative, as long as it's linear in the function or its derivatives, then that's considered to be a linear differential equation. So generally then we would say a linear ordinary differential equation of order n is going to have this kind of form here. So there's the highest the highest derivative here, and then all of these guys are linear in terms of the function or its derivatives. And the same definitions will apply to partial differential equations. All right. In this course, we're going to be dealing primarily, almost exclusively, with linear differential equations, which will be much easier to solve. So let me just run through some examples to make sure you get that. So I want you to look at these examples on the left here and tell me what the order is and whether or not it's a linear or nonlinear differential equation. So look at the first one here. You see Well, okay, so there's the second derivative of y, the first derivative of y, and both of those appear linear. They don't pair squared or some transcendental function involved. Just for these guys, they are all linear. And the highest order, of course, is second order. So this is a second order differential equation, and it's linear, right? Okay, next one. Here you see there's the first derivative of y with respect to t, and here we see y squared. So the highest order is the first derivative, and what you also see is that y shows up squared. It's not linear in y. So what we have is a first order equation that's nonlinear. All right. Another example, here we see the highest order is the second derivative here, and you see it shows up linear in that, linear here, but here it's showing up squared. So that means it's nonlinear. So we have a second order equation and it's nonlinear. Okay, couple more examples here. In this case, we have the highest order is the third derivative. It's linear in that, it's linear in the first derivative, and it's linear in y. So that's a third order and it's linear. And two more. Here's a very simple one. This one is fourth order in the highest derivative, and then there's third order, second order, and first order, and then just the function y. All of them are linear, so this is a fourth order linear. And then the last one here is second order with the highest derivative, but now you see this transcendental function, sine function of y, that makes this nonlinear in y, so that's a second order and it's nonlinear. Okay, so that's it for this lecture. In the next lecture, we're going to continue on and we're going to look at concept of fields.